Number 5A. Three spheres of equal size are composed of aluminum, density 2.70 grams per cubic centimeter, silver, density 10.49 grams per cubic centimeter, and nickel, 8.9 grams per cubic centimeter. List the spheres from lightest to heaviest. So if they're equal size, meaning they have equal volume, the one that's going to be the heaviest is the one that's the densest. So the least dense would be aluminum. And the least dense is aluminum, the most dense is silver. Therefore, if you had the same, if say it was 1 cubic centimeter of each of these, the heaviest one would be silver. Three cubes are composed of gold. Okay, I can already see I did this as circles, but you'll have to roll with it. They gave me the density, 19.32 grams per cubic centimeter, 21.45 grams per cubic centimeter, lead 11.35 grams per cubic centimeter. List the cubes from smallest to largest. Okay, so density is a conversion factor that allows you to go from grams to cubic centimeters. In A, we put grams up in the numerator. In B, I want to put cubic centimeters up in the numerator. So if I divide by grams, the one with the largest denominator there would give you the least size per gram of the substance. So platinum would be the smallest sphere because it's the heaviest, and lead would be the biggest sphere because it would be the lightest. If we all had the same, oh no, we're not the same, right? We're going to be same gram amount. If I had 1 gram of each of these, the largest one would be the lightest, the least dense one. I mean, so I did the conversion, right, to kind of show what I'm saying. Say we had 1 gram of each of these. The one with the biggest denominator is going to give you the smallest volume. The one with the smallest denominator is going to give you the biggest volume. Right, so the biggest cube, again, cube, would be the lead cube. Oh, I got gold there. That's why. Let's get that out of there. Lead. Better. Okay. What is the length of a pencil in the following figure if the ruler reads in centimeters? Okay, so if the ruler is reading in centimeters, it's about my eye. It's about where I estimate that that last significant figure. So I can see for a fact that this little pencil is greater than 7 but less than 8. They give me a hash mark in between the two. I'm assuming that's 7.5. So I can basically, with this particular scale, only make an estimation to the nearest tenth of a centimeter. So my measurement would have 2 sig figs in this case. I'm certain of the 7. The ambiguity is the 10th position. My eye sees exactly 0.5. If I had a better tool, all right, so this is the tool we're given, right? We can only make an estimation to the nearest tenth of a centimeter. If I were given a better tool, one that gave me hash marks to the nearest tenth, I can make an estimation. Am I directly on the 0.5 or am I in between the 0.5 and the 0.6? I still see it as I'm directly on the 0.5. Nonetheless, the degree of accuracy, I can make an estimation using this new tool to the nearest hundredth of a centimeter. So this measurement would have had 3 sig figs. And that's how sig figs work. The measurement is only as good as your tool. All right, so all certain digits plus the first uncertain one. So if I'm trying to make a estimation as to how fast I'm going in terms of miles per hour, I look at the blue scale there, and I can see that, okay, I got 60 and 80, so the midpoint must be 70. I'm a little bit past that, so I can make an estimation to the nearest mile per hour using the blue scale. If I'm trying to use the kilometer per hour scale, I have more. It's a more spread out scale. I can make estimations in between each of the per kilometer per hour measurements. So I'm looking at this. I'm past the 100. I'm not quite to the 120. So I'm at 110. I guess every one of those hashes represents an increase of 2 kilometers per hour. So I'm past 112, 114, so I'm in between 114 and 116. No, I guess in a way, I'm looking at this. It looks like I'm directly in between. So I'd be 115. 115.0. So I'm looking at this. I must be wrong on this one. If I'm looking at this, let's try it again. If I'm looking at this one, to the nearest 10, 12, 14, and I'm in between. So no, I can only make an estimation with this scale too, be to the nearest kilometer per hour. I can't make estimations to the 10th. So there's only 3 sig figs in this measurement, not 4. So it'd be a 3 sig fig measurement in terms of miles per hour with this tool, because I can only estimate to the nearest kilometer per hour. Classify the following as a pure substance or a mixture. All right, well, this is easier, right? Pure substances are made of either compounds or elements. Mixtures are compounds and elements in the same proximity. For example, rice pudding, right, would be a mixture. You'd have rice and you'd have pudding. And since I can differentiate between where the rice particles are and the pudding is, it's heterogeneous. Seawater is a mixture, right? You got salt, and you have all kinds of different salts dissolved in seawater. Nonetheless, there is no difference between one sample of seawater and, say, a sample of seawater next to it. So it's homogeneous throughout. Now, magnesium, I know. Magnesium's an atom. Magnesium is a type of atom. So this is a pure substance. Crushed ice is a compound. It's made up of 2 different atoms, hydrogen and oxygen. We call it water, right? So ice is just solid water, so it's a substance, not a mixture. I don't know how this ended up here, but 112 is the same question, right? Except this time we're looking at air, tomato juice, iodine, and sand. Air is a mixture, nitrogen, oxygen, and whatever gas is mixed in there, but it's mixed evenly and the same throughout. Now, tomato juice, I can see where if you were looking at it in terms of like little pulp bits versus watery bits, so it's not the same throughout, but it is a mixture. Iodine crystals, again, that's an element. Iodine is the solid iodine would be in a crystal form. It's one kind of atom. Now, sand. Sand, if we're looking at it in terms of like beach sand would be little bits of rock, all mushed up. So if you look at it, right, little brown crystals, clear crystals, black crystals, heterogeneous, not the same throughout. You're gonna have to learn the chemical symbols for the elements, right? The different types of atoms. You don't have to memorize them all, but you have to know some. So sulfur, S, gold, Au, chlorine, Cl, copper, Cu, uranium is U, nickel is Ni, sodium is Na, aluminum is Al, and silicon is Si. So some of these are more obvious than others. Again, the periodic table was contributed by different countries with different words. For example, sodium. Why doesn't it start with an S? They're using a Latin term for sodium or actually, I don't know historically why it's Na, but it is. You just have to memorize it. Sodium is Na. It's not S something. Make the following conversions from Fahrenheit to Celsius, Celsius to Fahrenheit, Celsius to Kelvin. Yeah, I don't know. I'm looking at this problem, guys. We don't deal with Fahrenheit in this course. Fahrenheit is just used sometimes in engineering with building bridges here in America because, we're not all on the metric scale. So Fahrenheit is a common unit. It's not an SI unit. The SI unit is Kelvin. So you have to be able to do conversions from Celsius to Kelvin. That's going to be throughout the course. Fahrenheit we're just going to do as an exercise here, right? You use the conversion factor to go from Fahrenheit to degrees Celsius or degrees Celsius to Fahrenheit. Put that as an F. Capital F. Fahrenheit. Yeah, I wanted to go to Fahrenheit, right? So I plug into the equation and I can convert to Fahrenheit. So like I said, it's all we're going to do with this. We're not going to be looking at Fahrenheit in this course. Now Celsius, to Kelvin, these are parallel scales. It's just they start in different positions. So Celsius starts where water freezes. Kelvin starts where there is no molecular motion. So if you want to convert from Celsius to Kelvin, you just add 273 to whatever your Celsius temperature is, and that'll put you on the Kelvin scale. If you want to go from Kelvin to Celsius, you'd have to subtract 273 to get to Celsius. They wanted me to go to Fahrenheit, but again, it's just an exercise and nothing. We're not going to be doing that. We're going to be doing these conversions: Celsius to Fahrenheit, Celsius to Kelvin, Kelvin to Celsius. What is it? A cube of osmium. All right, so if it's a cube, it's the same length on all sides, has a mass of 76.31 grams at 25 degrees Celsius. What is the density? So what I need is a volume measurement. So length times width times height, right? If they're all the same, it would just be 1.5 cubed divided into grams. It would give me grams per cubic centimeter. 3, density of titanium is 4.51 grams per cubic centimeter. All right, so when you're given density, it's a conversion factor, a way to go from cubic centimeters to grams or grams to cubic centimeters. In this case, they want to know what the mass is going to be if I know what the volume is. So milliliters is synonymous with cubic centimeters. They mean the same thing. So if you're using density to go from to get to grams, you want grams up in the numerator and cubic centimeters in the denominator. So when I multiply across, everything cancels except for grams. So milliliters divided by milliliters, gone. Cubic centimeter divided by cubic centimeter, gone. And what I'm left with is grams. So multiply the numerators, divide by the denominators to get your answer. Oh, what do we have? 4 sig figs in my answer, so I'd have to round to 4 sig figs. I should say 4 sig figs in my measurement. So my answer would have to represent 4 sig figs. Oh, wait a minute. Oh, the density's in 3 sig figs. No, I don't want to do that. I rounded this one up. We don't have to do that. I'll just have it in 3 sig figs. Yeah, that should do it. Yeah, 3 sig figs. Better. I guess I don't know. Have to look. Say it rounded up. It was an 8, right? Must have been 7. So we'll round it up to this many grams. Now, damn it. I see it above it. It's right there. 4. Come on. Come on. 4. Good. All right. 3 sig figs, right? The density was in 3 sig figs. Density, benzene is 115 degrees Celsius. We have its density in terms of grams per cubic, in terms of grams per milliliter. Calculate the mass if I know what the volume is, right? So if they gave me the volume in liters, I'd want to convert that to milliliters. So there's 1,000 milliliters in a liter, and then multiply milliliters by the density, and that'll give me grams. So again, with unit conversion, dimensional analysis, we just write down with what we're given and then use conversion units to get to the unit we want.